You've seen this population model. Here you see the system of two equations with x1 as a function of t, x2 another function of t, right? The derivatives of each function is equal to the right-hand side of the equations. And here, the parenthesis t, this is omitted for each function, just to make the writing a little more nice and clean. So we usually do not put the t. So just for your information, just always recognize x1, x2 are unknown functions of t. And we know that x1 is the predator, x2 is the prey, and the assumption that A, B, C, D are positive constants. Yeah, so they are all positive. So this population model that you know already. But today I want to introduce a general way of representing such a system. So let's write the unknown functions as the component of a vector. So it's actually a vector of two components and derivative of the vector. So here we have the left side of the system. The right-hand side is another vector, right? So derivative of the vector. So we can put A x1 plus B x1 x2 and C x2 minus D x1 x2. So that is another form of the same system. So now we can recognize the form by simply define this vector x. If our vector x has two components, right? x1, x2, yeah, x1 as a function of t, x2 as a function of t. So then we can rewrite the same system. So with this notation, we can simply write the system into x prime. So this x is the vector. Yeah, vector valued function. Its derivative is equal to some vector, right? Some vector that depends on x. See, I can put capital X because let's just see that this whole equation, it is represented into derivative of a vector, derivative of the x vector, right? The left-hand side is just, the right-hand side is just another vector, which is denoted by capital X, another vector. But this capital X, this capital X, of course, is depending on the lowercase x. So as you can see here. So I'm going to, you see this x1, x2, right? So this capital X is actually first component of the capital X, second component of capital X, depending on this X vector. Because this capital X, which is a vector, we call vector field. it depends on this other x. So this is a new representation, and it's just another way to look at the system. So I'm going to put this arrow. So these two are the same. So we recognize derivative of a vector. So actually, when you look for a solution, you are looking for the x. So the x is a known vector valued function to be solved, to be found. So we try to solve for this x that will satisfy such a system. So now I want to introduce a terminology that is the definition of vector fields. So let's have a notation. So suppose we have an open set. Suppose here's this O, which is a subset of Rn. Yeah, so just, okay, let's write as O, which is a subset of Rn. This O is an open set. And a vector field on O is simply a function defined on this open set. So a vector field on this open set is just a function or a map. So let's call this map capital X. This capital X defined on the open set, which is a subset of Rn. So that means the input is a vector in Rn. The image is also a vector in Rn. So such a map that maps a vector into a vector. So the input vector is from the open set. The output vector is a vector in Rn. So this capital X So in the previous example, if we look at the population model and this capital X, if we assume capital X is just the right-hand side vector here, you see that takes in a vector X, right? So the X, which has two entries, X1, X2. So the input vector is from R2. Yeah. Actually from an open set in R2. So, and the image will be still a vector. You see, this is capital X, a vector in R2. So this capital X is simply the right-hand side of that system of two equations. But when we write it in the vector form, so this whole right-hand side is called a vector field. But in this case, we can see the open set O is a subset in R2, right? Because our capital X is a mapping from such an open set into also a vector in R2. Because you see this is a vector in R2. So that is the definition of a vector field. A vector field that is defined on an open set. So let me draw a little diagram to indicate the meaning of a vector field. So let's first show an open set. Suppose this is the O, the open set, which is in Rn, right? It is a subset of Rn. So that means you pick an element in the open set, it will be a vector. A vector in Rn. But for this vector, once you apply the capital X, so that after the map, then you will have a new vector. That means the image of the map will be a vector, again, in Rn. So from this to a set of Rn, so this is some image from X into mapped into a new vector in Rn. So this is again. So as you can see, the X is a vector in Rn. The image is again a vector in Rn, but so this X is just a mapping. Okay, so we want to write it into the component form. So let's express it in the component form just to get familiar with the notations. In the component form, so because our capital X, the image of this small x is a new vector. So we want to write into n components, right? This image is again in Rn. So we need to express it. For example, the first component, right, that can depend on x. Second component of the capital X, because the capital X is a vector in Rn, so we must have n components. And each one of them will depend on the vector X, where little x is from the open set. That is the domain of the mapping. And the capital X is the image of X. However, this image has n component, right? So xi is the ith component of the image. So it is, for example, when I is 1, it is the capital X1. That's the first component of the image vector. I is 2, that's the second component of the image vector, so etc. So we have up to n components for this image vector. So each component is depending on small x, which is depending on the input vector, and each component has a real value. So I could be 1, 2, all the way to n, because this image vector has n components. So this capital Xi, X are the component functions. Component functions of capital X. So yeah, so this now once we have a clear understanding of the notations, then we can study a very general system of n equations. So let's write a differential equation system. So if I have x, the vector, the derivative of the vector is equal to a vector field that depends on x. So here, the x, if I write in component form, it is a vector of n components. So each component is a function of t. So we can omit the t, so just write the component. So x1, x2, x3, etc. So we can express the x. Just keep in mind, each component is a function of t. So this overall, it is a vector value function of t. And its derivative means each components, we take a derivative. So this is a derivative of this vector value function. The right-hand side is, if we write in component form, that means the first component of the vector field, right? That depends on the small x. Or you can write depending on each component of the small x. Yeah. So the second component of the vector field also depend on this small x. Small x means it depends on each component of the lowercase x, x1, x2, all the way to xn. And then the last component of the vector field also depend on on that X. Yeah, so this is our X. Okay, so we have a system, and these two are essentially the same system. So I just want you to see that this, right, looks like one single equation, but lowercase x is a vector. So the derivative of the vector is equal to a vector field. And this in the component form. And they are the same. So same system, and just either in a single equation form or in the component form. Now, what do we mean by a solution of such a system of equations? So whenever we are looking for a solution, that means we are looking for a curve, alpha. So let's assume alpha in the place of x, right? So alpha has to be a vector valued function. So if I want to replace the x with a certain alpha, which we call alpha a solution, then alpha must satisfy the differential equation. So that means our alpha is a vector valued function in the place of x. Alpha's derivative is equal to the vector field at alpha. So that's our definition of a solution of the system. So usually we call it a solution curve. So to make it more precise, so solutions of the system which we were looking at, that is this x prime equals certain vector field at x. So solution of the system are such a curve. So whenever a curve is a that means our solution curve alpha has to be differentiable, because you see alpha's derivative has to be equal to the vector field evaluated at alpha. So in order for alpha to be a solution of the system, alpha should be differentiable. Yeah, so let's first require alpha to be differentiable. So our curve actually we can first define a curve in Rn, because our alpha is a solution curve. So it's a solution curve in Rn. It is simply a map. It's just a map. What map? It is a vector, right? It is defined on t, a time interval. So we can see that this vector, each component of the vector is on the time interval. That means the vector is defined on as a time-dependent vector. Yeah, so from a time interval to Rn. Because our alpha, okay, we can often write as this one, alpha parenthesis t. So it is actually from a certain interval. T is defined on from a certain, for example, time interval. It mapping into from I to Rn. So because alpha is a vector valued function. So such a curve. If alpha is differentiable, then this curve is called differentiable curve. So here we need to require that alpha, in order for alpha to be a solution, first condition is that our curve alpha should be a differentiable curve. So that is the first condition for alpha to be a solution. So alpha should be differentiable curve so that this equation is defined. And then second, not only it is differentiable curve, the alpha should satisfy the equation. So that means the alpha's derivative is equal to the vector field at alpha. So the second, we need to make sure that for all t, that is for all t, all time t from this interval, our alpha at t has to be in the domain of the vector field, because otherwise, so if your alpha put here, so recall that if your alpha is this x, right, at place of x, that means it has to be in the domain of the vector field. Otherwise, the right-hand side is undefined. So we have to make sure for whatever t, x at t is in the domain of the vector field. So that's the condition for alpha to be a solution. So alpha at t has to be in the domain of a vector field, which is denoted by O, the open set. And another thing is, okay, now we are very glad that, okay, first of all, your alpha is differentiable curve, right? It is a vector valued curve, which is differentiable. Second of all, the alpha at t for n and t in the I interval, this alpha of t is in the domain of the vector field. So the vector field is defined. That means the whole equation is defined. Then with all that, then if our alpha satisfies this alpha derivative equals the vector field at alpha, then Right. So if this is true for all t from that interval, because t is in a certain time interval. So if this is true for all t in that time interval I, then our alpha is called a solution of the differential equation system. So that's our definition of the solution.